Okay, in Lesson 1b today, our student outcomes are the following. Students should be able to define appropriate quantities for a situation, choose the scale and the origin for the graph the piecewise function, and also understand the relationship between physical measurements and their representation on a graph. I am not going to do the first page today because it's just a video clip. We will do that in class tomorrow. So you can move on to the second page and we'll start there. Okay, example 2, an elevation versus time graph of a person's motion. So if I take a look at this graph before I look at the question, I see my y-axis is elevation in feet, my x-axis is time in minutes, and it's just an elevation versus time. Can we describe what the person might have been doing? If I look at it, elevation's increasing, then staying the same, increasing, staying the same, decreasing, and eventually gets back down to 0. Couple things that could be happening. Maybe we're traveling in a car. We're going up a mountain, staying the same in the elevation, going up the mountain more, staying the same, and going back down the mountain, and eventually back down to an elevation of 0. Maybe it's a person hiking on a trail. They're going up for a while, then staying constant, going up for a while, staying constant, and then they're going back downhill, back to the same elevation they started. Or climbing a tree. You go up the tree, you sit on a branch for a little bit, you continue to go up a little further, you're sitting on a branch for a while, then you need to come back down, you get stuck for a little bit, you're almost to the bottom, and then you jump right off, you jump down. I'm sure there's other ones you could have for describing what the person could have been doing. What is happening in the graph when it's increasing, decreasing, constant over time? I talked about it already, but I chose the person hiking. When the elevation is increasing, maybe they're walking up a hill. When the elevation is decreasing, maybe they're walking down the hill. When the elevation is constant, they're walking on a flat surface. But you could do that for either one of these other two pieces as well, and I actually talked about the tree already. What does it mean for one part of the graph to be steeper than the other? So we'll notice right here, this part of the graph is steeper than this part. What does that mean? That means they're going up quicker than they were in the beginning. Let's see what I have written here. The person is climbing or descending, this one's a pretty steep graph, faster than in the other part. So that's steeper than this is increasing, so it's descending faster than they were ascending earlier. Is it reasonable that the person moving up and down a vertical ladder could have produced this elevation versus time graph? Well, let's look back at it. It takes a time of 10 minutes altogether. So a person could be on the ladder for 10 minutes. But look at this. They are constantly going up the ladder, but it takes them about 3 minutes or 4 minutes to go 10 feet. Okay? That's not that far. So it's probably not going to happen. So it says the person is going up 5 feet in 2 minutes. That's that 5 feet in 2 minutes mark right there. That's an average rate of 2.5 feet a minute. That's probably too slow, so they're likely not going up the ladder. Possible, but not likely. Is it possible for someone walking on a hill to produce this elevation versus time graph and return to their starting point? So we've already talked, yes, it's possible to go up the hill, but do they return to where they started? If it is, describe what the hill might look like. Yes, it is possible. The hill could have a long, winding path with a gentle slope that zigzags to the top, then a shorter, steeper path to the beginning, back to the beginning. And I know my picture's not that good, but I'll show you with an arrow. So at first we'll say they're starting right here. They're going up. Their elevation's increasing, but it's increasing slowly because they're on that winding path. And they get to the top, and then they descend the hill pretty quickly. And towards the end, they get back to their starting point. And that's kind of what it shows right here. If I think about it, a slow winding path makes their elevation increase slowly. Then they can stay up at the top of the hill for a little bit, and then they descend quickly. And then back they descend quickly, and then towards the end it's kind of slower, back to a beginning elevation of where they started, so it is possible to start in the same exact spot that they actually started in. What do we use for the average rate of change? That term is slope. What was the average rate of change in a person's elevation between 0 minutes and 4 minutes? Well, at 0, their elevation was 0. At 4 minutes, their elevation was 10. So my average rate of change is change in elevation over change in time. My slope formula is delta y over delta x. I ended at 10 feet, but I started at 0 feet. I ended at 4 minutes, but I started at 0 minutes for between 0 and 4 minutes. Subtract and reduce, it's 5 feet per 2 minutes. Or 2.5 feet per minute. What does the horizontal piece of the graph mean in terms of slope? That means the slope is 0. Change in elevation over time, the horizontal piece up at the top of the mountain, that should have been horizontal up here, their elevation's not changing. So the change in elevation over 0 is 0 over time. 0 divided by time is just 0. We just saw in example 2 that it represents elevation over time. What are two measurements that are not represented in this graph? Speed. How fast is the person going? How quickly are they speeding up or slowing down? That's acceleration. How far did they go? Horizontal distance, total distance. And there's other things as well you might be able to come up with. You only needed 2. What type of equation would be required to create this graph? Linear. Linear are straight lines, and if we go back to your graph, we drew all straight lines. So you would need linear equations to create the graph. You can probably hear my daughter in the background. She's playing. Closing. Piecewise defined linear functions. Given non-overlapping intervals on a real number line. A piecewise linear function is a function from the union of intervals on the real number line that is defined by possibly different linear functions on each interval. Wow, that seems difficult to understand. So let's pick out some pieces on it. What you are really doing is you're putting pieces of lines together. They cannot overlap. If they overlapped, they would not be a function anymore. And we'll get into more in the future on what a function is. But for now, you can think of a function as each x value only has one y value. So again, just to review, pieces of lines we put together that are not overlapping, and if they overlapped, they would not make a function anymore. All of the graphs we studied today could form straight lines. Therefore, they are piecewise linear functions. Remember, there were no overlapping pieces. What we are going to do is look at these two graphs and decide if they are piecewise functions, why or why not. So I'm not looking where the graph is dotted. I don't care about that. I'm looking at the dark piece of the line. All of these are linear lines, straight lines. They do not overlap each other. So yes, the pieces don't overlap. On this one here, if I don't include the dotted parts of the lines, that is a linear function. They are all linear lines, straight lines. They do not overlap, so they are piecewise linear functions. Now some of you might be saying, wait, that dot and that dot overlap each other. Remember, the open circle means you don't include that point. So really, yes, this point is there, but you don't include it. So it's defined at 1, it's defined right here, but not here. And same thing at an x value of 8. The only dot that counts is the closed circle dot, not the open circle dot. Do this question tomorrow in class. Okay, we're going to finish up with this one. Number 2 says create an elevation versus time graphing story for the following graph. So if I look, the graph is increasing in elevation, staying constant, decreasing in elevation, and actually gets negative. Staying constant, increases back to an elevation of 0, and then stays constant after 10 seconds. Okay, so one thing that could be happening, maybe it's a squirrel's path, and think of it this way. Squirrel's going up the tree. He's grabbing a nut. He's running down the tree, and he's going underground to bury the nut. He's burying the nut. He gets back out from under the ground and is sitting on the sitting on the grass. Or a diver. Feet. So the diver goes up a ladder, stands at the edge of the platform, getting ready to jump, jumps in. When it hits the water, that's ground level. When he or she goes under the water, that's below ground level. Sits on the bottom of the pool for a couple seconds, and then comes back up and is just sitting even with the water in the pool, like treading water. Or how about a dog or a cat in the house? Now this one is a little more difficult to think about. Maybe the dog is jumping on the couch and going to the top of the couch, something like that. It's sitting on top of the couch, but then jumps off the couch and runs to the basement, or I guess jumps off the couch and into the basement. Starts going downstairs into the basement, sits downstairs for a minute, then comes back up the stairs and is sitting on the elevation of 0, so just sitting on the floor. Something like that. I'm sure there's other ones you can come up with, but those ones all work for this particular situation. Tomorrow we'll work on the other problems in class.